Looking at the sun cannot be good for you, but I don't blame you. Isn't the sun just so nice and warm and beautiful floating in space? Not like I know. I haven't seen the sun in months. That reminds me of a tangent that could last a whole video. Am I the only one who has no idea what heat is? I mean, I know what heat is, but I don't know what heat is. Like, I get that hot things have heavily excited particles composing them that vibrate and zoom around quickly and stuff, but is heat the average kinetic energy these particles have? No, that's the temperature. Oh, heat is the total kinetic energy of these particles. Well, in some circumstances that's the case, but that's mostly referred to as the thermal energy. I've come together with a few definitions actually, like heat is undefined and proves the law of conservation of energy, and heat being microscopic work. However, I think the main and most widely used definition is heat being the transfer of thermal energy until two bodies reach equilibrium, or have equal temperature. And I find that interesting because it explains a title I've never understood. The heat death of the universe describes a universe whose accelerated expansion left all in a cold, desolate void. I always thought it was the heat space death of the universe. Like, the universe died of heat. But no. At the end of everything, after even black holes have evaporated, there will be no transfer of energy because in this desolate wasteland, where even iron stars have decayed due to quantum tunneling, and nothing is left but spare photons and electrons flying around, each individual particle having its own observable universe of void surrounding it. All matter infinitely spread out as dark energy expands evermore. Everything humans have ever done, said, wrote, experienced, gone without a single trace. This expanse of utter nothingness, abyss, slightly off track. Everything is equally cold, not hot. Yeah, there is no heat because everything is practically equal temperature and completely isolated, so there is no transfer of temperature or thermal energy. Or any energy. But how does it get like this? Entropy. And follow along here. Entropy, causes heat. So really I'm asking how heat is transferred, what are the mechanisms? Because that's, the entire point of this video. Conduction! This is the most boring one. It sets ground rules on how heat works, which I will explain, but it's not too interesting. Wait, stay with me. I'm sorry, it's very, very interesting. Just less interesting because later in the video is even better. Keep watching! Heat is transferred through contact, or conduction. Hot things transfer thermal energy to cold things until they reach equilibrium. There's a bunch of math that describes how this will play out, but basically the fast molecules hit the slow molecules until they both reach a speed in between. Here's a fun little illustration I made. The speed of a molecule determines its color, from slow blue, fast red, and in between green. Watch as these hot and cold objects combine and reach equilibrium. By the way, the molecules are supposed to be circles, but my wonky physics engine decided that circles will slow down randomly, even though I made the simulation perfectly elastic. Here's one but with heavier particles. Remember that equilibrium is not based on average speed, but average kinetic energy, which is dependent on both speed and mass. Although the heavier particles are moving slower, they still have the same temperature because they have greater mass. So yeah, hot objects touch cold objects until they have equal temperature. Fast molecules hit cold molecules until they have equal kinetic energy. That's basically it. Let's ignore the math for this one. Convection. This is the transfer of heat in a fluid, and it's dependent on the fact that hot fluid rises because it becomes less dense. Assuming there's a heat source at the bottom, the fluid near it will heat up and rise, getting replaced by cold fluid. Cold fluid will heat up as the hot fluid cools down by conduction, or the other mystery secret method of heat. So then now cold fluid will sink as the now hot fluid will rise, in a loop that continues as long as the heat source is there. These motions form convection currents, and every component of this loop can be collectively referred to as a convection cell. Convection where fluid is heated by a flat layer below is called Rayleigh-Benard convection, and the cells are called Benard cells. I think they look cool. Convection is everywhere. Actually, all of these mechanisms are everywhere, but I'd like to highlight convection because it's less obvious to notice. Boiling water in a pot? Convection. Hot air balloon? Convection.
ocean currents? Convection. The Earth's mantle? Convection. The sun? Radiation.
No, I spoiled it. But also
Convection. Literally all of our weather? Convection. Okay class, let's go over a few terms. Natural convection is convection caused by heat only, no external forces except gravity. Natural convection is dependent on the fact that hotter fluids are less dense and thus more buoyant, so the denser fluid above it falls to the bottom. But that only happens if gravity is acting upon it. Forced convection is the opposite, when external forces are acting upon the fluid, like a fan. Forced convection doesn't need gravity. Internal convection is when a fluid is surrounded by a hot solid, like a boiling pot of water. External convection is when a hot solid is surrounded by a fluid, like the Earth and the atmosphere. Steady-state convection is when each individual point has the same properties over time. The actual matter is moving, but at a given position, the temperature, pressure, density, and other properties will remain unchanging over time. This is not the case for transient or unsteady-state convection. Individual points' properties change over time. An example of this would be convection with two immiscible fluids like oil and water. At this point right here, during one moment it has a density of water, because there's water there. And at the next it has a density of oil, because there's oil there. Advection is a transfer of something through a fluid, and convection is a form of advection, but the thing being transferred is heat. So yeah, the heat moves up as the fluid moves in a circle. I can make a whole video on convection and how it affects weather. But I won't. Yay, we made it to my favorite one, radiation. It's like when the sun makes you hot, like when you go outside. Yeah, I wouldn't know. All of this thermal radiation takes the form of electromagnetic waves, or light. It travels in a vacuum, goes fast, carries the electromagnetic force, all that good stuff. I'm sure in school you've heard that infrared radiation is the one that heats things up. But why that wavelength specifically? There's a whole spectrum, but only this wavelength heats things up. That's not true. All wavelengths heat stuff up at least a little, but why does infrared do this so efficiently? Well, the answer is that the infrared spectrum matches the natural frequency of vibrational oscillations within molecular bonds, causing quantum resonance to amplify the energy of the molecule. Don't worry, you're not supposed to catch any of that. I'll actually explain now. Molecular vibration is the oscillation of molecular bonds within a molecule. When atoms are bonded, they aren't affixed a distance from each other. They get closer and farther, like a spring, oscillating back and forth in a wave. Radiation is a wave too, so when it hits these molecules, it adds energy and makes them vibrate with greater amplitude. This vibration could turn into movement through collisions with other molecules and some other quantum stuff. This makes sense and all, but it doesn't quite explain why infrared is the only one. Well, these atoms oscillate at a certain rate, their natural frequency. In order to efficiently transfer energy from a wave, an object must have a matching natural frequency of the wave. This is called resonance, but because atoms are small, this is quantum resonance. If the electromagnetic wave is too energetic, it either won't be absorbed at all or it hurts the bond. If the EM wave isn't energetic enough, it simply won't have enough energy to amplify the molecular vibration notably. So it just happens that infrared is in the sweet spot, that the natural frequency of molecular vibrations of most substances is within the infrared part of the spectrum. This is also how microwaves work. On the EM spectrum, microwaves match the natural frequency of water. Nope, that's not true. It's a common myth that microwaves work that way, but they utilize alternating electric fields. Basically, light is a field of electricity and magnetism, and because it's also a wave, they move back and forth a lot, creating alternating electric and alternating magnetic fields. These alternating electric fields are disturbances that can affect charged particles. Now, polar molecules like water with a positive and negative end, and ionic compounds like salt with a positive cation and negative anion will get pushed around by these fields. Positive charges will get pushed one way, while negative charges will get pushed in the opposite direction, causing these molecules to rotate rapidly, especially considering that the electric fields alternate billions of times a second. This rotation causes bumping of molecules, converting rotational movement to translational movement. The bumping then heats everything up and stuff, and this entire process is called dielectric heating. There's also dielectric loss, which occurs when these rotating magnets release radiation, heating the dipoles up even more. What was I talking about? Oh yeah, so microwaves use microwaves, a form of light, and metal to reflect it everywhere in the box. All of these alternating electric fields make water, sugar, and salt rotate like crazy, heating everything up with this chaotic motion. Photons can also just hit the atoms to make them move fast, so... Okay, so radiation can heat up matter via resonance. Wait a second. I should probably explain how photons can transfer momentum even though they have no mass. Momentum is dependent on mass, we've all heard it, but light has no mass. Well, momentum isn't actually dependent on mass, it's dependent on energy. Mass is energy and light has energy, so light can transfer momentum to atoms, causing heat. Okay, so radiation can heat up matter via resonance, dielectric heating, and collision, but can matter release radiation? Yes! Because of some quantum mechanics stuff, molecular vibrations and atom movement can be just enough to transfer its energy to an electron moving to a higher energy level. Then the electron falls back down to its original state, releasing a photon. Although there are only set energy levels for electrons and thus the photons that are released, since all the atoms are close and meshing, the energy levels overlap into a bunch of smaller sub-levels for each, effectively becoming a gradient. Because the atoms in any substance with any temperature are naturally moving, all matter above absolute zero releases these photons, or thermal radiation. Basically everything in your life releases infrared light, which can be explained by something called blackbody radiation. Physicists wanted to imagine a perfect blackbody that absorbs all light, reflecting and transmitting none of it. That way, all measurable light emitted is from thermal radiation released by the object. It turns out that the frequency of light emitted is dependent on temperature only, and although blackbodies aren't real, the light real objects emit are the same as the light blackbodies emit if you ignore reflected and transmitted light. So every object between -200 and 500 degrees Celsius radiates infrared light, which is basically everything. This is also why hot metals glow a visible light. The hotter something is, the higher frequency light is emitted. Pause to look at this blackbody chart to see temperatures and corresponding light radiated. That's practically everything, but there are still a few things that are relevant enough to heat to land in this video. Friction! Don't we all hate friction? For one reason or another. It ruins a perfectly elastic world that is so easy to comprehend, and it's also pretty much the mediator between kinetic and thermal energy. No object is perfectly smooth, so when objects are, for example, sliding on each other, these tiny ridges and welds that each object has collide with each other. These collisions bump the molecules around, exciting them, which is heat. Micro collisions are friction. Macro collisions are collisions. And the force of impact causes the molecules in both objects to vibrate faster, which is heat. Phase changes occur when an object changes its state of matter, like from a liquid to a gas. A unique property of heat is that when converting from one state to another, all thermal energy is spent on breaking or making the bonds between molecules instead of continually increasing temperature. For instance, if boiling water is heated, it will stay at 100 degrees Celsius until all of it is gas, then the temperature will increase. The states of matter are solid, liquid, gas, plasma, which is when the electrons in a gas get so excited they escape the nucleus, Bose-Einstein condensate, etc. Look at this chart explaining the names from each state going to another, and this graph relating temperature and thermal energy during phase changes. And finally, we have the sun, which nuclearly fuses, where we started. Why is the sun hot? I'm sure you've heard that the sun fuses hydrogen into helium, but how does that release radiation? There's this thing called the mass defect, which is when nuclei weigh less than their constituent parts. This is because nuclei have less energy and thus are more stable than their individual parts. If not, then the baryons would just spread apart to be in the most stable state. It turns out that the product is lighter than the original reactant in the sun's fusion process. This mass doesn't just go away, mass is energy, with a coefficient of the speed of light squared, so extremely energetic gamma rays are released. Radiation, heat. This mass and thus energy difference is also nuclear fission, how nuclear bombs work. Yay, that's heat. You learned, I learned, we learned about the transfer of thermal energy and its various methods. I'm supposed to put a satisfying concluding sentence here. Please subscribe to my new channel and like this video. I put a lot of work into these, so please encourage me to make more by supporting me. Wink wink cough cough subscribe! No, seriously, I spent copious hours on this. There are so many animation challenges that I've had to overcome. I literally had to learn trigonometry to make this video. Please, I am so genuinely desperate. Please support me. Please, please, please.